Okay, so I recently implemented this paper in PyTorch, and because it's so fresh, I decided I'd record my understanding of it for my own purposes, and also hopefully it will be helpful for you. So this is aggregating nested transformers, and the architecture, or the way they name the architecture is like this: nest, right? And the first sentence of the abstract really helps me get started here, because it says the whole purpose of the paper in a nutshell. So, although hierarchical structures are popular in recent vision transformers, they require sophisticated designs and massive data sets to work well. The first vision transformer, the original one, the idea there was like, can we abstract away from the inductive biases that are present in convenets? So that's the translational invariance, the hierarchical structure, right? Can we move away from that and just use this very powerful model, the transformer, and apply that to vision? And the answer was, okay, with a lot of data, yes, it can work. And then ever since then, because we know that we need lots of data to make that work, and we're not actually leveraging the inductive biases that we know we could leverage, is what are the improvements we can make to this? And one of the ways that some of the papers have been trying to do that is by implementing these inductive biases somehow, bringing them into the transformer, and one of those being the hierarchical structure. By the way, by hierarchical structure we mean this. So like if you think of the standard MNIST case, right? So this is a number 9, right? And this is 28 by 28 MNIST, check it out. If we put this through a convolutional neural network that's trained already, what we might find is actually, if we look at the first few filters, we'll see that they're much like the types of filters that we're used to from classical computer vision, right? So maybe you'll get a filter that's designed to capture vertical edges, one that's designed to capture horizontal edges, one that's designed to capture corners, and then when you actually look at the feature maps that come out of this, you'll get like vertical edges, horizontal edges, and then you'll get corners, etc. But then when you get deeper into the network, you'll see that the kernels, the convolutional kernels, don't seem to have any resemblance to what we're used to handcrafting, and also that the activation maps that come out of that are just a bunch of inactive neurons with some active ones. So it's saying something higher level, right? Not low level like here's an edge, but something high level that we don't quite understand actually. And actually even the receptive field of one of these kernels, because it's like maybe 3 by 3, is 3 by 3 pixels. But when we get deeper, the receptive field of these convolutional kernels, even though they're 3 by 3, they're kind of aggregating information from more and more of the image. So the receptive field of this might be like basically the whole image. So what we're saying here is that we're going from like okay, let's look at the individual low-level features and look at the local pixel interactions, if you will, right? But as we get deeper, if we look at the local of the local and the local of the local of the local, we end up looking at the global in the end, right? And we're looking at higher level concepts rather than features, right? So we go local to global. That's what's meant by this, right? So here they're stating the problem that they want to solve, right? And then the solution is the proposed method nest converges faster and requires much less training data to achieve good generalization. And not written here explicitly because it's leveraging these hierarchical structures, or this hierarchical concept, right? And then actually they also, so that's the main meat of it. They also talk about using nest as a decoder, right? So an image generator leads to 8 times faster than previous transformer-based generation. And also they propose a novel method, and actually it's a novel method, but it's very specific to nest for visually interpreting the learned model, right? And by that they mean something like GradCam, right? GradCam is the best example I can think of, but the idea is, like, say you have a picture of like a cat, and our network predicts cat, and we want to know why the network predicted that in terms of where was it looking. And if we use the GradCam method, we can get like a heat map, which shows the various regions of the image that the network is looking at to make its prediction. So the source code for this, by the way, is available on Google Research, and also the PyTorch implementation that's available on PyTorch image models. Some of you may have used that, aka Tim, which you can find on GitHub and in PyPy, right? And actually in the description below this YouTube video. Okay, so the first thing, naturally, that they'll talk about, I think it's good to keep talking about this at the beginning of papers, is the original vision transformer. And you know, I haven't done a video on the vision transformer myself. I have done something on self-attention. You can check that out. And there's another great video and many more great videos on the vision transformer. I will go into it very briefly here, and I'll leave a link in the description for your browsing. So the vision transformer, and I'm assuming here that you're familiar with transformers in general, for NLP, really. Right, so imagine we take a 224 by 224 input image. What we want to do now is we break this up into patches. It'll become clear in a moment why we do that. And in the vision transformer original, they typically break these into patches which are 16 by 16 pixels by 3 channels. And then with that, you end up getting 14 patches along the top, 14 patches along the side, so you get a total of 196 patches. So the first bridge to what you typically think of in transformers is, let's unroll this or unfold this, or however you want to say it, into a 1D sequence of 196 patches. Right? And this is kind of like NLP. Mary had a little... So if this was NLP, we'd get word embeddings for each token in the sequence. Here we treat our patches as tokens, and we get patch embeddings through, you know, there's a bunch of ways you can do it. So you can maybe just like unfold this into like a 1D vector. So 16 by 16, 256 by 3, 768, right? Unroll all of this into a 768 long vector, and then apply some sort of transformation to that. And there are other ways you can do it, right? Usually with a learnable component, but you end up with an embedding. And then I like to draw my transformers bottom up, so we'll actually redraw this sequence down here. There we go, sequence, right? And then the first thing that you do is you do multi-head self-attention. Right, so what that essentially does, in a nutshell, again, you can check out my other video on this as well, is each of these embeddings gets the opportunity to communicate somehow with all other embeddings, and based on the responses they get, and with themselves, and based on the responses they get from the other embeddings, make it like build up a heat map. So maybe this one here builds up a heat map, a normalized to one heat map of like how important each of the other embeddings are for the decision it's currently about to make. And then based on that heat map, it aggregates, you know, all the information from the other patches, and then projects that forward. That's the multi-head self-attention. But the key point here is that it's a global interaction. It allows this patch to know about what's happening here, or maybe it allows this patch to know about what's happening here, 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 right? And then you get a feed-forward network, and then this constitutes a transformer layer, and then you build up more transformer layers, right? Another thing I didn't mention, but I should mention, is On top of these vectors, you add another vector of the same dimensionality, right at the beginning only, right? And one for each, right? And this is a positional embedding. And in the VAS1, in the original transformer paper, the positional embedding is a sinusoidal fixed embedding, but here it's learnable, right? And this just helps the network keep track of the relative positions of these, especially because this wraps around in 2D, right? So you want the network to somehow know that this is right adjacent to this, even though that's, you know, the 15th patch in the sequence. And you know, they do find that it's exactly what is learned in the end. So that's one component that makes this work for vision. The other one is that we have to add another token here, the class token, or another patch. Not a patch, it's a token, right? And this token, by the rest of the network, is treated the same as all other tokens in terms of the way that the self-attention is done. So this is incorporated in that self-attention calculation, and it moves up along with the rest of the patches. Whoops. And then at the top here, we kind of do away with this. We don't care what's here. But this, again, remember, this is actually just a vector. And for this, we apply a linear transformation with a softmax nonlinearity to get to another vector with 1,000 elements for the 1,000 classes of ImageNet, if you will. And you know, maybe one of these is cat, right? And when you do backpropagation with cross entropy loss, you backpropagate through this, and by virtue of the multi-head self-attention, you know, the backpropagation makes its way through the whole network. I think that's everything I wanted to say about this. That's it in a nutshell. One last thing is the way that this scales with image size, or the number of operations and the number, not the number of parameters, but the number of operations scales with image size, because you know, in order to do all pairwise interactions, which I mentioned before between these, and if this sequence length is n, then you need n squared interactions. So if you make this image larger, then, I mean, if I make this image, like, if I make this image twice the size, so we go to 448, right, then n goes to n squared already, just because we have n patches here, and then when you make this twice the size in one dimension, you get n squared patches overall, and then on top of that, you have n squared interactions, so it scales to the power of 4 with the edge length of the image, right? The number of interactions that need to be computed. So that's also important. With that out of the way, back onto Nest. So again, they mention, okay, so lack of inductive bias is what's important, is what's holding back VIT models, right? And this is super key right here. For me, this is one of the biggest key motivations for why you would do what they're doing in Nest, and other papers that look at hierarchies and trying to replicate this idea of a hierarchy, is that the bottom layers attend locally to the surrounding pixels, and top layers favor long-range dependency. So what they're saying is, even though this vector here has the ability to talk, there we are, to do these interactions with all the other positions, with a trained vision transformer network, they find that in the end, it only ever interacts with the ones near it. And the ones near it, I mean actually in a 2D sense. So this patch in the lower layers of a trained VIT only interacts with these nearby patches and not with these. It can, but it doesn't. It just doesn't end up doing that in a trained version, right? And then at the very top, you end up getting global interactions. And in the middle, you kind of get something in the middle, right? Interactions which are larger than totally local, but not totally global. And then this reminds us a lot now of what was happening here, right? Where you started with local interactions, you end up with global interactions. So it's convenet-like, and then the other thing is it saves us a lot of computations, because remember I said about the scaling, right? If we can somehow, put a lot of the computation, with the lower layers, if we can somehow think of like hand coding this so that we restrict attention to be localized into different subsections like this, or if you will, into different blocks, right? So I only want attention to be happening here, and this can't attend to this, for instance. And then I only want self-attention to be happening within this block, and then within this block. If we can do that, then we end up saving a lot of computation time, right? And also we satisfy this hierarchical constraint. And then the other thing is we already know from the observation of vision transformers that they end up doing that anyway, right? So that's the main point here. And so, Nest isn't the first paper to try to address this. Other papers have tried to address this as well, and I'll let you have a look at them in your own time. And they actually do mention this quite a lot. Swin, this is. So that's this link here, right? But they're saying that the way that they do that is with quite sophisticated designs. Right? I'll show you why Nest is nice and simple. So here they kind of summarize everything I've been speaking about, and I always love these sections in the paper. These are our main points kind of thing. Now that we've spoken about the vision transformers, let me kind of extend that now to what they're doing specifically here, the main architecture for Nest. So rather than read through this, I'm just going to draw it all for you. This is a good reference. So again, starting from bottom up. So we have our image. There we are. Oops. There we go. We have our input image. Now what we're going to do, like I mentioned before, is we're going to break this up into blocks. We'll call them blocks, right? Where we want the self-attention mechanism to be local, right? And what they do for ImageNet is they ended up breaking up the first hierarchical bit into, there we are, 4x4 blocks, right? But you can actually do this into 8x8 or 16x16, right? But they ended up doing 4x4 blocks. And then what we do is we do exactly what happens here, right? But only within blocks. And actually, so again, I'll just tell you, this is later in the paper, but they divide this up into 4x4 patches, right? And because it's 4x4 patches, this ends up having 196 patches in total. This one as well, 196 patches in total, right? And actually, so this, by the way, if you look here, they're just trying to represent what I'm saying here. So B is the batch dimension, right? Tn is the number of blocks, so it will be 16 for us here. N is the sequence dimension, or the number in a sequence, so 196, right? And D is the dimension of the embeddings that I mentioned up here, right? So I don't know what it was exactly. There are many variants, but let's just say 768. Okay, and then to this you apply a bunch of transformer layers, just like you do in VIT, except that the self-attention is divided out into 16 blocks, and so patches within this block can only attend to patches within this block. Patches within this block can only attend to patches within this block. By the way, this is now reshaped. It's flattened out, right? It's flattened out and then rearranged such that all of the patches here ended up here, all of the patches here ended up here, etc. Right? So you do all that, and then you end up here again. And I'm just going to draw this same thing from down here, but I'm going to draw it shorthand, 4x4, right? You end up with this, right? Again, because again, this doesn't change the shape of anything, right? You propagate everything forward together. Now, the other key component here is then you add another layer called block aggregation. And specifically, it doesn't have to be, but they find out that this works really well. This is, first of all, a 3x3 convolution. Then it's layer norm. right? And then it's max pull 3x3 with a stride of 2. Stride 2. The main point of this whole thing, though, apart from the fact that they've designed it this way and it seems to work the best, but the main point is this: the stride of 2. Because what you end up doing is you end up collapsing this down into a feature map that's half the dimensionality of this one, right? So then it ends up looking like this instead, right? And what you do with the blocks is in order to account for that, is you actually have, you actually have 2x2 blocks instead of 4x4 blocks. And because you've accounted for it already, then now there are the same number of patches, 196 per block, right? And then you do the same thing again. So you apply more transformer layers to this. But now, as you can see, like if your input image was that of like a person, whereas here, a block has this kind of domain, right? So the attention mechanism is localized over this portion of the image. Up here, if we just look at the same image again, and now we're thinking about concepts like perceptive field, the perceptive field of this block covers this portion of the image, so a larger portion of the image, right, than it did before, or than one block did before. So anyway, you end up adding putting a bunch of transformer layers here. Then you still have a block you still have like a feature map which has 2x2 blocks in it. And then you apply the block aggregation again. And then you end up having, so I'm going to draw this up here now, this, but because there was a stride 2, you end up having just one block. Also with 196 patches in it. By the way, like if it's not clear to you why there's 196 patches exactly still, that's okay. You just need to get a pen and paper and play around with it, and you get it. I had to play with it a bit. And then with this, you end up doing more transformer layers, but then you don't do a block aggregation, right? Because you're done. You're at the end. And then with the VIT, you had like a class token alongside everything, but no, not here. Here, remember, this is just a bunch of vectors. Right, so this is 196, a sequence 196 long, bunch of vectors. By the way, it was always 196. No, it wasn't. But this is just a sequence 196 long. And what you end up doing is you take an average pull, as you would in a convenet, right? And then you get one vector, right? Which has the dimensionality of the model, which may have been 68, for instance, right? That's that D down here. And then with this, you do your old, transform this to however number of classes you have, so 1,000 maybe, softmax, and then you get your cat out, or your dog, actually. There we are. I want to be fair to dogs and cats, actually. I should be more representative of dogs in this sort of talk. Okay, so this is pretty much it in a nutshell. And the rest of this talk will just be kind of going into some of the particularities of that, and what it does, and what the results are. So let's see what's next. So we've gone through this block aggregation for mixing information across blocks. Okay, and then they talk about the image generation, which I mentioned before. I'll just spend a very short amount of time on this. So they flip what I said before. They flip it around, so they go from top to bottom, right, to do image generation instead. And then instead of block aggregation, they have, coming back down here, they have, I think they're calling it block deaggregation. Somewhere in here, I think they call it, there we are, block deaggregation. And then they kind of, instead of doing a stride 2, which is a downsampling technique, they upsample or unsample, if you want to call it that, using pixel shuffle, which you can check out. And that's it. The section for that is quite short, actually. Right. And then finally, the other thing that they mentioned was this kind of method that's akin to GradCam, which helps you like kind of visualize heat maps of like where the information is coming from when you make a certain decision. So I really like this. I think it's pretty cute. So the idea is like, again, so you have this vector which comes out with 1,000 classes, and it's dog, right? And then this came from like a single block, right? Which in turn ended up coming from a 2x2 set of blocks, which in turn came from a 4x4. And this tree traversal is like, what if we ask ourselves the question, let me just draw this one. Ask ourselves the question, which block is most responsible for the dog, right? And what we do is we actually start from the top and we ask ourselves which block, well, this is the most responsible block because it's the only one. Then we ask ourselves which block is responsible the most for what's in this one, or most responsible for dog. And then we ask ourselves again which block down here, and that will have to be in the top right 4 here, is most responsible. So maybe this one, right? And the way we answer that question is by looking at the derivative of dog. Let's get the color back. Derivative of dog with respect to the activations, right? So if we pick like an activation here, we can calculate, if we nudge this activation up or down a little bit, what will happen to the probability of dog in this vector here, right? And by what amount? So there's a negative sign here. I didn't bother sitting down and thinking about why it's negative or positive. I'll let you do that. But the idea is that the magnitude also is very important, right? And then the sign is something you can figure out after. But the higher the magnitude, the more important a particular activation is in determining the outcome. And so you can actually do this for all of the activations of all of the patches here, right? And then you can global average across this whole block. And you can do that here as well. So you can come out with a figure here, 0.78, 0.1 something, right? And you can normalize if you want. And then you pick the strongest one. And then you do that again. And this is what they've got in this picture here, which is really cool. But instead, they've actually instead of just having a dog, they decided to be very representative of both dogs and cats and have 2 dogs and 2 cats in the image. And show you with arrows. So we start in the middle because we start with that 1 by 1. Oops, again. Here we are, 1 by 1, right? And then we move to somewhere in the 2 by 2. So this is what's happening here, right? Because this is like that. And then after that, we move to somewhere in the 4 by 4, right? Which is here, right? And it's actually showing you the scores. So, you look at all 4 classes in turn, and you do that same exercise with each of the classes. So this type of spaniel, don't know how to say that. This is how important the 1 by 1 is. This is the value of that derivative that I mentioned before, d dog by dA, average pooled over the whole block. And then for all of the 4 blocks, block 1, 2, 3, 4, this is, you get 1.02 here. Pick a color that works. 1.02 is the value of this, right, or the magnitude of that. 0.5 here, 0.31 here, 0.48 here. So this one wins, and so you traverse down to here, and you've already gotten that, because we know what the input image is. We know it's pointing to the dog, but then you can go further if you want. So that's pretty cool. I think they have some pictures down here with like actual heat maps. Yeah, so like this is for, well, this was one where it kind of went wrong. It ended up pointing at this kind of light source here for lighter, where the lighter is literally sitting here. But I don't know. I don't know what to say about that. It's just cool. And then the mouse, look, it's pointing at the mouse, so it ends up pointing to this quadrant, and then it points to the mouse. and then the radio telescope, and then a wooden spoon. Oh, that's so fun. I like that. Okay, so back up here. Okay, so that's the whole theoretical part. I'll go through the experiments and point out bits that I think are interesting. So let's just change color. There we are. Okay, so actually, so I've never spoken about, through this lockdown and stuff. I've been doing most of my deep learning journey during the lockdown, so I haven't really spoken to people about this sort of stuff verbally. So I don't know how to say this, but I'll just say CIFAR for now, and maybe someone can correct me later. So the CIFAR results, they train this up just on the CIFAR data set. That's the ImageNet one, CIFAR, there we are. And they compare it to a handful of different transformers that have full attention. And then the SWIN transformer, which has local attention using shifting windows, and some convenets. These are actually convenets that are specifically optimized for CIFAR, and they're not named. And they compare the results, and they end up finding, as is often the case, that they have some of the best results in this table. And yeah, so you can definitely see that they are definitely better than the data efficient transformers and the other full attention transformers. Kind of on par-ish with the convenets, and on par-ish, a bit better than the SWIN transformer. And with CIFAR, I think you could correct me if I'm wrong here, but it's somehow like there's less data just because they're smaller images, right? And it's easier to overtrain on. So the effect is really pronounced of using this kind of hierarchical approach over the full attention approach in terms of how good the performance is. Oh yeah, and there's the C10 as well. Yeah, but what I always find more interesting, and I jump to in papers, is the ImageNet, and here, so the full attention transformers perform much better than they did in CIFAR, and obviously the data efficient transformer performs better than the VIT because it's kind of figured out some of the issues with the data efficiency. But then SWIN and Nest are kind of head and shoulders above these, and comparable to some of the convenets, or better than some of the others. But still, SWIN and Nest are pretty close to one another, and in terms of flops and params as well, there's not a huge enough gap that I'd say one's better than the other, particularly in all cases or whatever, or head and shoulders. But I think the point of the paper is to say that they managed to do what SWIN does, maybe better, but importantly, with a much simpler architecture. Oh, and that's something I forgot to talk about up here, and I just really briefly wanted to point to it. The code implementation of this. So when I implemented this, I realized the only kind of sophisticated or annoying bit to implement is changing from the perspective of you have this 2D map to this perspective where you have a sequence, right? And the reason that's annoying is you can't just flatten this directly. It's because you need to kind of, when you flatten it, you need to make sure that all of these end up here and all of these end up here, etc. So that's the only annoying bit, going in and out of that. But then the actual the self-attention is super easy, right? So with normal self-attention, and if you have this will make more sense if you've actually looked at the code for self-attention, but if you have a tensor, which is batch, number of the sequence dimension, and then the number of channels, the numbers, the size of the features, right? Then this might be your query key, right? And then your query vector, and your key vector will also look like this, right? And then when you actually do query key transpose, when you compute this in code, you just transpose these last two dimensions, and then you go q at k dot t transpose, right? You transpose these dimensions, and then you end up going B and C matrix multiplied with BCN. BCN, right? And you get a B and N matrix tensor out from that, right? And then this case where actually instead of having B and C, you have B, T, and C, where T is the number of blocks, right? And that's your query vector. Your key vector will look the same as that, and you still do the same thing. You just transpose the last two dimensions, and you apply a matrix product over the last two dimensions alone. But then what's happening is it's localized because just imagine if you just had this as your whole batch dimension, really. So you're just doing it separately for each block and separately for each batch. So there's a lot less flops there. Anyway, back to those results. So as I was saying before, it's Swin and Nest look on par-ish. But the key point they want to drive home with this, for instance, is the data efficiency of Nest, right? It's more data efficient than the data efficient transformer. So this is what does the ImageNet accuracy, validation accuracy look like after a certain number of training epochs? And these two curves here are the data efficient transformer, and this is Nest. So Nest obviously does a lot better with less training. So even after 60 epochs, you're already sitting at 80 plus ImageNet accuracy, which is pretty awesome. What I would have liked to see, and I couldn't find through a cursory glance, was Swin and where it sits on this. But I'm actually assuming that it would sit close to where Nest is, right, if not the same. What's also interesting, and I'd like to know more about it if I could, was where this goes with more training. But something that we do know, and that the authors do mention at some point, is that if we actually do this with more data, so if we do this with ImageNet 22K, for instance, instead of just ImageNet 1K, DEIT wins, right? And this, so if you were to plot this ImageNet accuracy with a constant number of epochs, but amount of data here, accuracy, right? Nest would plateau off, and a DEIT would keep growing. So they do acknowledge this, and it's because DEIT doesn't use these inductive biases; it just uses the sheer power of the transformer, right? And then the other interesting point they make here is, okay, in terms of like being data efficient, when we do augmentations, one of the reasons we do that is to kind of make it as if we have more data. So if we remove augmentations, it's as if we have less data than we would kind of figuratively had with augmentations, if that makes sense, right? So okay, so the baseline with all the proper with all the augmentations that they normally train with is this for a selected data efficient transformer and a comparable Nest. But if we remove, like for instance, cut, mix, and mix up, data efficient transformers lose 6 points, whereas Nest loses 1.7 points. Right? It loses way less because we remove that augmentation. Same thing for RAN augment. And I'd love if someone could tell me in the comments why data efficient transformers go down to nothing when you remove random raising. Let's see what else is here. Okay, and this is super interesting, I find. So this is relating to that block aggregation. And if you remember what it was going from top to bottom. It was a 3x3 convolution with stride 1 and padding, and a layer norm and a strided max pool, 3x3 max pool, stride 2. And they wanted to justify why exactly they did it that way. The first thing is they compare this one, the one that they actually end up using, with just the convolution, which is strided, just patch merge, which you can look up. I'm not sure what that is exactly, but I think it's written somewhere here, and just an average pool. And they find that this combination works the best specifically. And more interestingly for me is they find that it works better on the image plane than on the block plane. And let me show you what that means. So when you apply that convolution, yes, here it is. You could apply it to the blocks one by one individually, and then this is a padding of 1 outside the block, right? And then so because of the stride and max pool, this ends up becoming the size of one block. This one too, this one as well, and then you end up getting, instead of 16 blocks, you get 4 blocks. Or you can apply it to the whole image plane, if you will, where you take all these blocks and put them together, and now convolutions get to overlap different blocks. And what happens here is you get this extra information exchange between blocks. And I mean, I've been trying to reason through why this is so helpful. Like, it's a huge help in some cases, but because, yeah, the idea is that you get some information exchange between blocks, but after you, so say you have 2 by 2 blocks, right? And then you do the aggregation, you get to 1 by 1. Well, after that, you have a bunch of transformer layers, right? And the transformer layers mean that you get global interaction everywhere anyway. So I'm not entirely sure why this particularly having a convolution which does some information transfer between blocks right before the aggregation is so helpful, because after the aggregation you do talk between blocks, if you will, right? Because the blocks are now merged into one. One way I've tried to think about this is, okay, so you have your 2 by 2 blocks, and then there's a lot of global interaction within each block. Global locally within a block. And maybe these interactions can be designed such that it pushes the necessary information at this resolution, right, to the edges, specifically the edges where there's another block nearby, right? So I imagine this is the way the network learns things. It learns to push relevant information that needs to be communicated to other blocks towards the edges, because after that you end up having this convolution which overlaps and has this communication, or brings that information that's been translated to the edges and communicates it amongst the blocks. And that kind of mechanism is a little bit different from this self-retention mechanism. And the other part is that this is higher resolution than when this is happening up here after aggregation. But still, it's quite interesting that it helps so much. What else? Impact of block aggregation, we've covered that. Nest hierarchy variance. So they tried different depths. For ImageNet, they used 3. They used patch size. I thought I said 4 by 4, but maybe it's 2 by 2. No, it's 4 by 4 for sure. It says somewhere else for ImageNet. But that's not interesting. I've already spoken about that. What is kind of interesting here is they talk about, the effect of trying different depths. And when I say depth here, by the way, I mean the number of pyramid hierarchies there are. So for the one I've been talking about so far, there are 3, right? There's the 4 by 4, the 2 by 2, and the 1 by 1, right? And that's the one that they use for ImageNet, but they use varying depths for CIFAR, which is what this is based on here. And they show that having a depth, well, actually, if you think about a depth of 1, that is exactly VIT, because there's no block aggregation which happens. A depth of 2 is the next step up from VIT, where you have 1 block aggregation. And what they're claiming is that, okay, you start to introduce that, and it's not enough. It's not enough to for the effects of the kind of hierarchical structure to really materialize. But then as you add more layers, you get better results, because now you're actually manifesting this hierarchical structure that they've come up with. And then finally, the performance declines. I think there was a point on this somewhere, perhaps, but I don't remember exactly where. You can check it out. maybe drop it in the comments if you can find it as well. I will leave the results of the Decoder experiments for you to have a look at. Generative modeling, yeah, so that's this section here. And actually, honestly, maybe it's because I haven't actually looked at this metric a lot myself. So if I were to speak about it, I wouldn't be very informative. Visual interpretability. So they talk more about the visual interpretability, but I'll leave you to look at that because I've done that bit, I believe, enough so far. And finally, so they close with raising some of the questions that I may have raised before. So one, and questions they acknowledge they haven't answered. So will the local transformer design limit the scaling effectiveness to billions of training data? I did think they mentioned that somewhere. That's why I said they say plateaus. Maybe a Control F would find that for you. You can look at that later. And how much can Nest improve core vision tasks like detection and segmentation? Because the trend in these papers is you always have or often have sections at the end where you then try to do this with detection and segmentation. And I think it'll be pretty easy for Nest, by the way, because with the vision transformer approach, you're stuck in this. Better use my mouse to scroll. You're stuck in this paradigm of being in a flat 1D sequence the whole time. But with this, you're kind of dipping in and out of the sequence view and the image view, and because of that, actually the TIM library, the PyTorch image library, does extract the features at each stage. So it would be easy for you to then tie into that and do like an FPN structure if you want, to try to do like some detection. So that's it. I think Nest is really, I would say, elegant the way that it's done, and that's what they're stating. They don't use very sophisticated, difficult building blocks to make it happen. It cuts down a lot on the flops required, and it makes training this transformer more like training like a convenet on ImageNet. It wasn't clear to me that the performance was amazing compared to other variants that try to do similar things like Swin, for instance. But I think there are it's a great academic exercise, and because of its simplicity, I suspect structures like this could be used in the future. Yeah, thanks very much. Leave comments if you're interested. If you want to ask questions, check out the TIM library, and maybe I'll do more of these. We'll see. Thank you.